Harish E. Now we are going to see about logic gates. What is logic gates? Logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. The relationship between the input and output is based on a certain logic. Based on this, logic gates are named as AND gate, OR gate, NOR gate, and etc. etc. Now we are going to see about AND gate. The AND gate performs a logical multiplication commonly known as AND function. The output is high when both the inputs are high. The output is low level when one of the inputs is low. A circuit which performs an AND operation is shown in the figure. It has n numbers of input and one output. Now we are going to see about the truth table of the AND gate. It is an easy operation where we can find the output is 1 when both the inputs are 1. If either one of his input is different, then the output will be different. Now we are going to see about the OR gate. The OR gate performs a logical addition commonly known as OR function. The output is high when any one of the input is high. The output is low when both the inputs are low. And the truth table. It is the easily known for addition. When you add the input table, when you get 1, the answer will be 1, output will be 1. That's it. Not gate. Not gate is also known as inverter. The output is high when the input is low. The output is low when the input is high. As we mentioned above, the truth table shows the inverse of the input. When the input is 0, output is 1. Input is 1, output is 0. Now we have seen the basic gates. Now we are going to see about the universal gates. The universal gates are NAND and NOR gate. Now we are going to see about NAND gate. The NAND gate is the contraction of and NOT. The output is high when both inputs are low and any one of the input is low. The output is low level when both the inputs are high. The truth table, as it said above, when both the inputs are 1, the output will be 0. That's it. NOR gate. The NOR gate is the contraction of OR and NOT. The output is high when both inputs are low. The output is low when one or both inputs are high. Now the truth table. Now by seeing the truth table, you can see like it was like both the inputs are 0, the output will be 1, and the others will be having this output as 0. Now we are going to see about the exclusive gates, exclusive OR and exclusive NOR. Exclusive OR gate. The output is high when any one of the input is high. The output is low when both the inputs are low and both the inputs are high. It shows that there are different values of the inputs having one as output. If the values of the inputs are same, then the output will be 0. Now, exclusive NOR gate. The output is high when any one of the output is high. The output is low when both the inputs are low and both the inputs are high. From this truth table, we can see that the input values with same values as the output 1. If the values are different, then the output is 0. Thank you. Hi, I'm Harish E. Now we are going to see about half adder and full adder. Half adder. A half adder is a combination circuit needs two binary input and two binary output. The input variables designated the AND 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 bits. The output variables produce the sum and carry. The half adder can be implemented with an exclusive OR and an AND unit. Now we see the truth table of half adder. We have two inputs and two outputs. When we give input as 0 and 0, we get output for carry as 0 and sum as 0. When we give 0 and 1, we get carry as 0 and sum as 1. When we give 1 and 0, we get carry as 0 and sum as 1. When we give 1 and 1, we get carry as 1 and sum as 0. And we gain of adder. We have two formulas, one for sum and one for carry. The formula for sum is a dash b plus ab dash. The formula for carry is ab. And here we see the circuit diagram of adder. Now we are going to see about the full adder. A full adder is a combination circuit that forms the arithmetic sum of input. It consists of 3 inputs and 2 outputs. A full adder is useful to add 3 bits at a time. In full adder, some output will be taken from exclusive OR gate. Carry output will be taken from OR gate. Here we see the truth table. Here we give 3 inputs and get 2 output. When we give 0, 0, 0 as input, we get carry as 0 and sum as 0. And 0, 0, 1 as input, we get carry as 0 and sum as 1. When we give 0, 1, 0 as input, we get carry as 0 and sum as 1. When we give input 0, 1 and 1, we get carry as 1 and sum as 0. When we give input as 1, 0, 0, we get carry as 0 and sum as 1. When we give 1, 0, 1, we get 1 as carry and sum as 0. When we give 1, 1 and 0, we get carry as 1 and sum as 0. When we give 1, 1, 1 for all the inputs, we get carry as 1 and sum as 1. Here's the K-map for full adder. Here also we have two formulas, one for sum and one for carry. Here's the formula for sum. A dash b dash c plus a dash b c dash plus a b c dash plus a b c. Here's the simplified version of the formula. C of a dash b dash plus a b plus c dash of a dash b plus a b. And the formula for carry is ab plus bc plus ac. And here's the circuit diagram of full adder. Hi, I'm Harish and now we are going to see about off subtractor and full subtractor. Off subtractor. The off subtractor is constructed using exclusive OR and AND gate. The off subtractor has two inputs and two outputs. The outputs are difference and borrow. The difference can be applied using exclusive OR gate. Borrow output can be implemented using AND gate and an inverter. Truth table. As you can see here, we have two inputs and two outputs. When the inputs are 0 and 0, the outputs we get are borrow as 0 and difference as 0. When the input is 0 and 1, we get borrow as 1 and difference as 1. When the input is 1 and 0, we get borrow as 0 and difference as 1. When the inputs are 1 and 1, we get borrow as 0 and difference as 0. Now we are going to see about the K-map of subtractor. We find the K-map and build them using two formulas, one for difference and one for borrow. The formula for difference is a dash b plus ab bar dash, and the formula for borrow is a dash b. And here we see the circuit diagram of subtractor. Now we are going to see about full subtractor. The full subtractor is a combination of XOR and OR and NOT gate. In a full subtractor, the logic circuit should have three inputs and two outputs. The two off subtractor put together gives a full subtractor. The first off subtractor will be 0 and AB. The output will be different output of full subtractor. The expression AB assembles the borrow output of the off subtractor, and second term is the inverted different output of first exclusive OR gate. Now we see the truth gate. Here we have three inputs and two outputs. When the inputs are 0, 0, 0, we get borrow as 0 and difference as 0. When the inputs are 0, 0 and 1, we get borrow as 1 and difference as 0. When we have inputs as 0, 1, 0, we get borrow as 1 and difference as 1. When we give input as 0, 1, 1, we get borrow as 1 and difference as 0. When we give input as 1, 0, 0, we get borrow as 0 and difference as 1. When we give input as 1, 0, 1, we get borrow as 0 and difference as 0. When we give input as 1 and 0, we get borrow as 0 and difference as 0. When we give inputs as 1 and 1, we get borrow as 1 and difference as 0. Now we are going to see the K-map of subtractor. As we saw for the off subtractor, this too has two formulas, one for difference and one for borrow. The formula for difference is a dash b dash c plus a dash b c dash plus a b dash c dash plus a b c. Now for borrow, we see a dash b plus bc plus a dash c. And this is the circuit diagram.
Hi, I'm Harish E. Now we are going to see about code conversion, binary to gray and gray to binary. Title: Code is a symbolic representation of discrete information. Codes are of different types. Gray code is one of the most important codes. It is a non-weighted code which belongs to a class of codes called minimum changes code. In this codes, while transversing from one step to another step, only one bit in the code group changes. In case of gray code, two adjacent code number differs from each other by only one bit. The idea of it can be cleared from the table given below. As this code is not applicable in any types of arithmetic operation, but it has some application in analog to digital converters and in some input-output devices. Binary to gray code converter. Binary to gray code conversion is a very simple process. There are several steps to do this types of conversion. Steps given below elaborate on the idea on this type of conversion. The most significant bit of the gray code will be exactly equal to the first bit of the given binary number. Now the second bit of the code will be exclusive or of the first and second bit of the given binary number. That is, if both the bits are same, the result will be 0, and if the different, the result will be 1. The third bit of the gray code will be equal to the exclusive OR of the second and third bit of the given binary number. Thus, the binary to gray code conversion goes on. Objective: Gray code system is a binary number system in which every successive pair of numbers differs in only one bit. It is used in one application in which the normal sequence of binary numbers generated by the hardware may produce an error or ambiguity during the transition from one number to the next. Input and output variables. The 4-bit combination assigned to binary code will create 4 bits to represent a decimal digit. There are 4 inputs and 4 outputs. The input variables are defined as B3, B2, B1 and B0, and the output variables as defined as G3, G2, G1 and G0. Here's the truth table. We use the K-map to plot the truth table. Here's the circuit design. Gray code to binary converter. Gray code to binary conversion is again very simple and easy process. Following steps can make your idea clear on this type of conversions. The most significant bit of the binary number will be equal to most significant bit of the given gray code. Now, if the second gray bit is 0, the second binary bit will be same as the previous or the first bit. If the gray bit is 1, the second binary bit will be altered. If it was 1, it will be 0, and if it was 0, it will be 1. This step is continued for all the bits to do gray code to binary conversion. Objective: the most significant bit of the binary code is always equal to the MSB of the given binary number. Other bits of the binary output can be obtained by checking gray code bit at the index. Input and output variables. The 4-bit combination assigned to gray to binary code, 4 bits to represent a decimal digit. There are 4 inputs and 4 outputs. The input variables are defined as G3, G2, G1 and G0, and the output variables are defined as B3, B2, B1 and B0. Here's the truth table. The game of here's the circuit design. Hi, I'm Harish. Now we are going to see about encoder and decoder. Encoder. An encoder is a digital circuit that performs inverse operation of the decoder. An encoder has two n input lines and n output lines. In encoder, the output lines generates the binary code corresponding to the input value. In octal to binary encoder, it has 8 inputs, one for each octal digit and 3 output that generates the corresponding binary code. In encoder, it is assumed that only one input has a value of 1 at any given time, otherwise the circuit is meaningless. It has an algorithm that when all inputs are 0, the outputs are 0. The 0 outputs can be generated when d not equal to 1. Combinational design procedure. An encoder is a combinational circuit that performs the reverse operation of the decoder. It has a maximum of 2 power n input lines and n output lines. It will produce a binary code equivalent to the input, which is active I. Therefore, the encoder encodes 2 power n input lines with n bits. Objective. The other routine tasks are mentioned on the encoder resume as follows: filling and organizing data, preparing and sorting data, reviewing data to ensure accuracy, entering data from paper to computer systems, completing data backups, filing and making paper copies, checking work for any duplications, reporting to management about errors, and keeping a record of data entry and database information. Here's the truth table. And here we see the logical diagram of encoder. Decoder. A decoder is a multiple input, multiple output logic circuit which converts coded input into coded output, where input and output codes are different. The input codes generally has fewer bits than the output code. Each input code word produces a different output word. That is, there is one-to-one mapping can be expressed in truth table. In the block diagram of the decoder circuit, the encoder information is present as n input producing 2n possible outputs. 2n output values are from 0 throughout 2n minus 1. Combinational design procedure. Determine required number of input and outputs for the specification. Derives the truth table for each of the outputs based on their relationship to the input. Simplify the Boolean expression for each output. Draw a logical diagram that represents the simplified Boolean expression. Objective. A decoder is a digital circuit that detects the presence of a specified combination of bits on its input and indicates the presence of that code by a specified output level. A decoder is a circuit that changes a code into a set of signals. It is called a decoder because it does the reverse of the encoding. But we will begin our study of encoders and decoders with decoders because they are simpler to design. Here is the truth table. And here we see a logical diagram for the decoder.